I know this lecture is not the most titillating, and if this were a lab-based version of the course, this wouldn't have been a lecture at all. It would have been some lab exercises. But we'll end on a slightly higher note when we talk about Java libraries. Now that we know about packages, we'll be able to use all these amazing things that are provided for us in Java. So before I get there, I want to back up and talk a little bit about what we've done recently, right? So we talked about implementation inheritance and what it does for us and why it's so useful. And one of the main things we've done so far is we've understood how it is that we can implement what I'll call an abstract data type. And I'll give a definition in a bit. So in lecture, for example, I created a list61b interface, and then we created a couple of specific implementations of list61bs. Okay? So what this does for us is we're able to specify to the world, hey, these are lists. There exists a thing known as a list61b, and by the way, here are a couple of implementations. Likewise, on project 1b, you created a deck interface. In project 1a, you created a deck interface and then a couple of implementations. And again, the miracle of implementation inheritance means people can use your decks without knowing exactly what's underneath the hood, right? So they could, in principle, just use decks, much like we did in project 1c, and we did the palindrome, right? You were supposed to just use a deck, not a particular deck, okay? So I guess I should say that we had SOA. That wasn't a word. Anyway, we also had a side story in the last couple weeks, which was another thing we can use implementation inheritance for. So one thing is this notion of capturing an abstract data type, but we also used it to specify a contract for a behavior that all classes that implement some interface should obey. That's more generic. So for example, if we want to specify that dogs can be compared to other dogs, we could create an interface called rComparable. Dogs could implement this, and our day would be done. And now, if anybody wanted to compare generic things instead of dogs, right? If we wanted to write a maximizer class, like we did in lecture, we could now build a maximizer in terms of rComparable. Okay. So in other words, the punchline is simply that we used interfaces to specify something that a dog is capable of, right? And we also saw, as another side, that we can use interfaces as a way to do a crude version of what might be called a higher order function in Python, right? So in older school Java, before Java 8, it was extremely, in fact, it was the only way you could really do something like compare two characters in a special customized way would be to create an interface that says, all right, this is a character comparator. You can compare characters, and then you can make your own implementations. Now in Java 8, you can actually, there are things like lambdas that you might know from Python. You can bind function to variables, but we're not really going to talk about it in our class, though I will have some optional slides and an optional lecture if you do want to learn about that, but it won't be one of the core pieces of the course. So in this way, we can use interfaces to containerize, I guess, functions, right? A place that you could pass around a function, okay? But back to that big story, right? The main story. So I mentioned this notion of abstract data type. So a data type is just a type like you might declare, public, class, yada, yada. And an abstract data type is going to be a data type which is defined by its operations, but not by its implementation. So we can have a double-ended queue, and it can have a bunch of operations, like you can add first, add last, check if it's empty, check the size, and so forth, without actually having any notion of whether or not it's an array or a linked list. And here are a couple of implementations. So these are implementations of our abstract data type. Why do we care? Well, abstract data types, actually, there are lots of them. There's all kinds of cool things you can come up with other than just a double-ended queue. So here's an example, a stack, right? So suppose we have here it has two operations. These are the two things that a stack can do. You could push integers onto the stack, in which case they'll go to the top, and we could pop and they'll go away. So if I have the number 4 here and I push the number 6, it appears on top. If I now push yet another number, there it appears too. Yeah, that's the push operation. So you keep stacking them up. Pretty fun. We also have the pop operation, where we can remove and return the top item. So if I call pop, 2 gets popped off, and this method will return 2. Okay, so a question to think about. So hopefully the idea of a stack came up, right? So it turns out stacks are extremely useful, and we'll be seeing a little bit of why in Project 2 if you do the optional extra credit. Now that we understand what a stack is, I want you to think for a moment, which one do you think will be faster? Would a linked list or an array-based stack be faster? Okay, so in my opinion, I think it's a pretty good opinion, linked list is just a better solution for this problem, right? Why? Why isn't an array as good? Well, an array is not as good because if we use an array-based stack, we're going to have to be doing some resizing. So resizing is a little slower, okay? So I think linked lists will be overall faster, okay? So that's an example of another abstract data type and how linked lists and arrays might trade off, or how they might compare for implementing a stack. Okay? Here's another one. It's called a grab bag. So what is a grab bag? Well, it supports inserting. You can throw stuff into the bag. So imagine you have here, I have a Triscuit box. Get that. Okay. So I have a Triscuit box, right? And I can insert things like a sock. Not really a place for it. And I can put these keys in there and whatever else. And then I can remove things. And when I do remove, I get a random item. Maybe I get the sock. I can also sample, where I can look in there and see whatever's on top. And that'll change every time. And lastly, I can ask for the number of items in the bag. So the question then is, what do you think will be faster now? Okay, so I'll wait. Okay, so I'm going to say in this case, let's start with linked list, which is, I'm going to say, not as good a choice. Linked list will be overall slower because if you want to remove a random item or sample randomly, at some point somewhere you're going to have to scan through the bag and pick something. So to randomly find something, you're going to have to, it's going to be a worst case linear time operation, as we'll talk about later. Okay? So if you dig through the bag, to get something randomly, it's going to take you linear time. By contrast, an array, if I want to get some random item, well, I know what the size is. So if I have an array and I just want to peek, like if I want to sample, I pick a random index and return that item. If I want to remove, well, in that case, I go to that random item and I get rid of it. Okay. Now, it might seem that you would need to shift everything over to fill in the array, but there is a clever solution. And I'll just leave that as a puzzle for you if you want to think about how can I make a grab bag with an array that is a constant time remove operation. That is, no matter how many items are in it, remove is very fast. Okay. So it's just a couple of abstract data types. So in this week's discussion, you got a chance to, and if you haven't done it yet, definitely see the worksheet, use different abstract data types to solve problems. Okay. All right, now that we know about packages and we know about abstract data types, I can tell you the wonderful, wonderful news that there exists the java.util package. So in class to date, we built everything ourselves. We had list61b, which I built in lecture. You built the deck. But it turns out that the java.util package has all of these things that we might want, like lists or sets or other fun stuff, right? It also has some abstract classes, which give default implementations for methods, just like how we had in list61b. This had a default print method. Abstract list has a bunch of things, okay? And then finally, though, the thing you care about most, it has some concrete classes, some actual specific implementations. You can say like new array list, new linked list, and produce them. Okay? These can be instantiated. Just as a quick aside, you may wonder why it is that we don't have this middle level of hierarchy. Why didn't we have that? Well, we built our list using Java 8 technology, where we had the default keyword, but these classes were originally created in the pre-Java 8 days when you could only provide default methods using an abstract class. If you want, actually, you can go Google and look at the source code of abstract list and see the kind of stuff it has in there. So here's, I had it open earlier. Oh, here it is. Yeah, abstract list. So this abstract list, you can see all the things it does. So here's an example of a default method, index of. And yeah, you know, the details here aren't really important, but just to give you a flavor, if you want to peruse the code, you can actually see what an abstract list is. Though now that I look closely, I realize I'm looking at Java 6, so it'll look a little different in Java 8. Okay, kind of a derail there. But the important point is you are given an interface list and a bunch of implementations, which is great. Okay. So the most important things, among the most important interfaces in java.util, are the things that extend the collection interface, which is stuff that holds, it's a set of interfaces that represent collections of things, right? So there's a list and a set and a map interface that all extend collection. Oh, by the way, interfaces can extend to their interfaces. So you can actually have a whole hierarchy of them. But, and so this one right here, for example, represents a list of things, a set of things, a mapping of things, so like a Python dictionary, or you might have also heard them called an associative array, an associative list, a symbol table. There's other names. These are going to be our champions. These are the things you're going to use all the time. Okay. So the most important thing, really, that you're going to care about for the next couple weeks while we're working on Project 2 is what list, set, and map do, right? What can they be used for? Lists represent lists of things, sets of things, maps, mappings. And I'll say that usually most programmers, right, they can get away without really knowing which implementation they're using or why, right? Novice programmers will just use array list everywhere, not really thinking about the fact that there's the word array there. And that was true in 61A, and it'll be true for the near future. But I will mention that once we're done with Project 2, we're really going to dig in deep and understand what all of these implementations are and the trade-offs that we get, kind of along the lines of what we did with GrabBack. Okay? So as a closing example of how we can use these kind of collections, let's just see what a map does. Okay? So if you know Python dictionaries, you basically know what's coming. I'm going to write something called character counter. And what it's going to do is it is going to will print out the number of each character in this file. It's going to look at itself. Okay? So what it's going to do is it's going to say n equals new n. I'm using that same class from Project 0, character counter.java. I'm going to fix this. Okay? And then we're going to say as long as this is not empty, we're going to process each character and start counting. Okay? One natural approach is to use a map. Right? In particular, what we're going to do is build a map which is going to be called, it's going to map characters to integers. I'm going to call it car counts. Okay? What is car counts? Well, I'm going to say it's a new, I don't know, hash map, character integer. And this is going to be a data structure we can now use to associate with others. So associate data of type character with integers. This is the equivalent in Python of doing this, create an empty dictionary. Okay? Now, because this is part of java.util, we need to actually import map and hash map. And from here, we can continue through and implement. Okay. So it turns out that in Java, if I want to, well, the first thing I would do is I would look at would grab the current character. Okay, current equals n dot read car, and then I would say while, or sorry, not while. I would say if it so happens that car counts contains key current, right? If the is the key in the current dictionary and the current mapping. If it's not, then I should add it. I'll say car counts dot add, and I'll put 0. Or sorry, I'll put current is 1. Okay. Let's write a comment here. If the character found has never been seen, add note that it has a count of 1. Okay. Now, if by contrast the dictionary does contain it, well, then what we want to do is we want to say old count equals car counts dot get current. Okay. Old count, or sorry, then we'll do car counts dot put or add, sorry, current old count plus 1. Okay. So in other words, if we write a comment here, if character is not found, increment its, or sorry, if character was previously found, it's count by 1. Let's make sure we didn't mess any syntax up here. It's quite possible. Okay, character or count. Oh, that's weird. Counter. Aha. Okay, still some bugs. Is it not called add? It's called put. So one thing you'll find when you're trying to use these classes, it's a really good idea. Like, you know, of course, usual Google thing. How put map Java, right? Or how add map, right? Sometimes you'll find yourself with the documentation, and you guys know most of what all this means now. So I can actually look and see, okay, it's called put, right? So that's the kind of thing. You want to make sure that you are looking at documentation like this, particularly in Project 2. It'll be handy. So car counts put current old count plus 1 and put here. So we compile, and it seems to be good. Though there's one final step, which is I want to actually also print out the character counts. Okay. So I do this, and I get, okay, these are all the counts. There were 2 exclamation points, there were 2 quotes, there were 12 left parentheses, 5 right braces, and so forth. Okay. So I was assuming, by the way, throughout this example, that you'd seen something like a dictionary. So in Python, this might have been something like if current not in car counts current car counts current equals 1. Like, this is what it would look like. That would be the equivalent of this. Now, if you came from E7 or something else, you might not have seen something quite like this, but you'll get plenty of practice soon. Okay. So that's the story, right? We now have these new abstract data types that allow us, we're going to unlock a huge number of these now, sets, maps, lists, whatever, that are going to allow us to do all kinds of very cool things moving forward. Okay, that's it for today. So I'll see you next time, and then I hope things are a little less dry, since, yes, not my favorite topic, packages and environment variables. But this stuff's cool.